Hi, my name is Pierre Chastenay, and along with my colleagues Emmanuel, Mohamed, and Simon, I'm here to talk about learning the seasons by analyzing data and modeling. What we want to do is teach the reasons for seasons. The seasons, as you know, is a concept present in most OECD K-12 curricula, but it's also one of the most difficult astronomical topic to learn in the classroom. To understand the seasons, like any other astronomical phenomena, students first need to gain enough experience with the phenomenon as seen from the surface of the Earth, the geocentric point of view. But they also need to gain experience in switching perspective between the geocentric and the space-based point of view, what I call the allocentric point of view. Fortunately, models or concrete models in the classroom can help students have this space-based point of view on astronomical phenomena. We also propose that to understand astronomical phenomena, students should do astronomy like astronomers do. So starting with a question and several hypotheses, students do their own observation, they analyze their observation, they create models, they use the models to make predictions, application, and then they communicate their models and their findings to other people. The problem with this approach is that it's very hard to observe the seasons. Seasonal change is very slow. It takes 1 year to complete. And so daily systematic observation of the sun's apparent motion across the sky can be very difficult for students. And so it proves to be impractical to conduct such a long observing program with K-12 students during a school year. But one can provide seasonal data to students for them to analyze and basically reach the same goals as observing the seasons themselves. What we did in this research is give students seasonal sun ephemeris data to students for two cities, Montreal in Canada and Coyhaique in Chile. Both cities are located at the same longitude and the same latitude, but in different hemisphere. And so in terms of seasons, Montreal and Coyhaique are mirror image of one another. So this is the kind of data that we gave our students. So they're basically sun ephemeris with sunrise times, sunset times, azimuth of sunrise and sunset, the height of the sun in the middle of the day, the length of the day, etc., etc. With this data in hand, we ask students a series of probing questions that for them to analyze the data that we've provided. And so these questions were basically to compare sunrise and sunset position on the horizon for Montreal and Coyhaique, compare sunrise and sunset times, the length of day, the height of the sun at noon, apparent movement of the sun across the sky on equinoxes and solstices, and also compare the climate between both cities for every month of the year. They were also encouraged to create graphs to supplement their answer and to create a visual memento of the information that they found. And so this is an example of the kind of graphs that our students created. This one was created with Excel. It's basically showing sunrise and sunset times for Montreal and Coyhaique. Sunrise is in blue, sunset is the red curve. And you can clearly see that Montreal and Coyhaique are mirror image of one another in terms of season. For instance, in June, when Montreal has the longest day of the year, it is the shortest day of the year in Coyhaique and vice versa. The next step in this teaching sequence was for students to create and use a model of the Earth and Sun to understand the mechanism between the mechanism behind seasonal changes. So basically we use a styrofoam ball with two push pins, one for Montreal in blue, the other for Coyhaique in red, a bamboo stick and a paper cup so that we could have this nice inclination of the axis of rotation of the Earth. And we used a small flashlight with a ping pong ball glued to the lens to create a diffuser, which was a nice representation for the sun. And so working in pairs, students use the model to try to reproduce the observations that they've come to by analyzing the data. And we also asked them to find out what was the seasonal change, for instance, for Mercury, which has 0 inclinations in terms of its axis of rotation, or Uranus, which has 98 degrees inclination. In terms of research, because this teaching sequence, we wanted to find out if it produced results in terms of learning gains. So we basically did the first iteration in a process of development research. That's what I'm presenting here today. It was a quasi-experimental design. We didn't have a control group, unfortunately, and we used a convenience sample of 37 pre-service high school science teachers that were enrolled in an astronomy methods course at the Université du Québec à Montréal, taught by my colleague Simon. 22 males, 15 females. You have the information about the mean age here. 25 students at the end of the day completed both pre and post-test questionnaire at 2-month interval. The instrument we use is what we call the Reasons for Seasons Concept Inventory. It's a 22-question multiple choice instrument that we've created ourselves by using questions drawn from 6 published instruments in astronomy education. And we've supplemented these questions with a few questions about the comparison between the northern and the southern hemisphere. When we've analyzed the data, we found that the Crumbach alpha for our test was 0.1815, which indicates high reliability and high internal consistency, which is good. But we didn't conduct a full psychometric analysis of the instrument yet. In terms of results, we looked at the learning about the seasons. Unfortunately, the data was skewed for the post-test. It was not normal, so we could not use a traditional t-test because normality could not be assumed. So instead, we use a non-parametric statistical test, the Wilcoxon sign rank test for related samples. And the output indicated that the post-test scores on the Reason for Season Concept Inventory were statistically higher than the pre-test score. The median was 18 on the post-test and 13 on the pre-test. And the z-statistics was significant to 0.001, which is good. Effect size is considered large at R equals 0.87, large or very large, depending on the scale that you use. We also had a question in our questionnaire about the confidence that the students had in their own answers. Again, the data was not normal, so we used the same non-parametric test. And we found that, again, there was a statistically significant difference between the post-test and the pre-test in terms of confidence, the confidence students had in their own answers, with z-statistics significant to 0.001, and again, a large to very large effect size. You have to keep in mind that there's several limitations to this results. First, it's only the first iteration in a development research process, so there's more to come. It was a small sample. It was a convenient sample. We didn't have a control group, so we cannot really generalize in terms of the results to other groups. Also, we suspect that part of the gains were caused by maturation over the 2 months period or out of school sources of information that the students might have look at. And unfortunately, we were not able to conduct a delayed post-test because it was the end of the term. So there you have it. Thank you very much. And I hope to read or hear from you if you're interested in this research.